How does a massive aircraft defy gravity? The answer lies in a counterintuitive fluid dynamic principle. High velocity flow correlates inversely with static pressure. Static pressure is the thermodynamic pressure exerted by the fluid, representing potential energy. Dynamic pressure, conversely, represents the kinetic energy of the moving fluid. Bernoulli's principle dictates that the total mechanical energy along a streamline remains constant. For an airfoil, air accelerates significantly over the curved upper surface. This faster flow results in substantially lower static pressure above the wing compared to the higher pressure beneath the wing. This pressure differential creates the net upward force known as aerodynamic lift. This mechanism demonstrates the fundamental conversion between kinetic energy and pressure energy, enabling flight and driving countless engineering systems. Bernoulli's principle is derived directly from the fundamental conservation of mechanical energy applied to an ideal fluid element. This principle requires that the total energy per unit volume of the fluid remains constant along any single streamline. This constancy holds true only when assuming no energy losses occur due to friction, known as viscosity, or due to heat transfer. The total energy comprises three distinct forms. First, pressure energy, represented by the static pressure P. Second, kinetic energy, represented by the dynamic pressure term, which is 1/2 times the fluid density ρ times the velocity squared. Third, potential energy, represented by the hydrostatic pressure term, which is the density ρ times gravitational acceleration g. The sum of these three specific energy terms defines the total head or total pressure of the fluid system. The mathematical statement of Bernoulli's principle is P plus 1/2 ρv squared plus ρgz equals a constant. P represents the static pressure, measured in pascals. The term 1/2 ρv squared is the dynamic pressure, quantifying the kinetic energy per unit volume. Here, ρ is the fluid density in kilograms per cubic meter, and v is the flow velocity in meters per second. The term ρgz is the hydrostatic pressure, accounting for the fluid's elevation z and the gravitational acceleration g. The sum of these three specific energy terms defines the total head or total pressure of the fluid system. The mathematical statement of Bernoulli's principle is P plus 1/2 ρv squared plus ρgz equals a constant. P represents the static pressure, measured in pascals. The term 1/2 ρv squared is the dynamic pressure, quantifying the kinetic energy per unit volume. Here, ρ is the fluid density in kilograms per cubic meter, and v is the flow velocity in meters per second. The term ρgz is the hydrostatic pressure, accounting for the fluid's elevation z and the gravitational acceleration g. When applying the equation to compare two specific points, labeled 1 and 2, along the same streamline, the full equation is written as P1 plus 1/2 ρv1 squared plus ρgz1 equals P2 plus 1/2 ρv2 squared plus ρg2. This comprehensive equation precisely quantifies the necessary trade-off between the three energy components: static pressure, dynamic pressure, and potential energy. Applying the standard Bernoulli equation requires four strict assumptions regarding the fluid behavior. First, the flow must be steady, meaning velocity and pressure at any fixed point do not change over time. Second, the fluid must be incompressible, requiring the fluid density ρ to remain constant throughout the flow field. Third, the fluid must be inviscid, meaning internal friction or viscosity is negligible. This assumption eliminates energy losses due to shear stress. Fourth, the equation applies strictly along a single streamline. It can only be applied across multiple streamlines if the flow is also irrotational. Real-world engineering applications must always incorporate empirical loss coefficients to accurately account for viscous dissipation and friction effects. In horizontal flow systems, the potential energy term, ρgz, is often neglected or cancels out, simplifying the relationship between static and dynamic pressure. Static pressure is measured by a pressure port oriented perpendicular to the flow direction. Dynamic pressure represents the kinetic energy available for conversion back into static pressure. Total pressure is defined simply as the algebraic sum of the static pressure and the dynamic pressure. Stagnation occurs at a specific point where the fluid velocity instantaneously drops to zero. At the stagnation point, all dynamic pressure is converted entirely into static pressure. Consequently, the pressure measured at this point is the total pressure of the system. Pitot tubes are instruments specifically designed to utilize this stagnation principle to accurately measure the total pressure and subsequently determine the flow velocity. The Venturi effect is the practical demonstration of Bernoulli's principle in constricted flow systems. When a fluid flows through a converging section, known as a throat, the cross-sectional area A decreases. The continuity equation, A1 times V1 equals A2 times V2, mandates that the flow velocity V must increase proportionately to the area reduction. This mandated velocity increase necessitates a corresponding decrease in static pressure exactly as predicted by Bernoulli's equation. Venturi meters are designed to measure the static pressure differential P1 minus P2 between the wide inlet section and the narrow throat. This measured pressure drop is directly proportional to the square of the flow velocity. Engineers use this relationship to calculate the flow velocity and subsequently determine the volumetric flow rate Q through the pipe. The primary mechanism for lift generation on an aircraft relies entirely on the pressure differential created by flow acceleration. The cambered or curved upper surface forces the air to travel a longer path, resulting in a significantly higher velocity compared to the flow beneath the wing. This higher velocity above the wing translates directly to a lower static pressure region precisely as predicted by Bernoulli's principle. The resulting pressure imbalance between the top and bottom surfaces generates a net upward force, which is the aerodynamic lift. While viscosity and the resulting circulation are necessary physical components for real-world lift generation, the pressure differential derived from the velocity difference remains the fundamental force component quantified by Bernoulli's equation.